My name is Dr. Mike Murphy. I'm an assistant professor of computer science and information systems at Coastal Carolina University. In this lecture, I'm going to discuss interrupts and device input-output. When hardware devices on a computer produce events, we need some way of being able to handle those events within the operating system and deliver them to applications. And hardware devices are going to produce events at times and in patterns that we don't know about in advance. For example, we don't know which keys the user is going to press on the keyboard until the user actually presses those keys. If a cat walks across the keyboard, we're going to see a completely different pattern of key presses from which we would expect to see with a human user. Similarly, if we have incoming network packets, if we're running a server application or even just a workstation, and we have messages coming in from the network, we don't know the order and timing of those messages. We also don't know when the mouse is going to be moved, or when any other of a whole bunch of hardware events is going to occur. So how can we get the information generated by these events and make it available to our applications for use? Well, we have two options. First option is that we can poll each device. We can ask each device if it has any new information and retrieve that information. Or we can let the devices send a signal whenever they have information and have the operating system stop whatever it's doing and pick up that information. This is called an interrupt. The polling model of input involves the OS periodically polling each device for information. So every so often, the CPU is going to send a message to each hardware device in the system and say, hey, you have any data for me? And most of the time, the device is going to send back, no, don't really have any data for you. Other times, the device is going to send back some data. It's a really simple design, extremely simple to implement, but there are a number of problems with polling. First problem is that most of the time, when you're polling, the devices are not going to have any input data to deliver. Thus, polling is going to waste a whole lot of CPU time. The second issue that occurs is high latency. If I press a key on the keyboard, that keystroke is not going to get transmitted to the computer until the next time the CPU polls the keyboard to ask which keys have been pressed. If that time is set to be really short, I'll have good responsiveness, but the CPU is not going to get any useful work done. On the other hand, if we set that time length to be long enough for the CPU to get some work done, there's going to be a noticeable lag between the time I press a key and the time a character appears on the screen. Since the device must wait for a polling interval because it can translate input, we're going to have a high latency situation. And again, shortening that polling interval to try to reduce the latency simply wastes a whole lot of CPU time checking devices that have no input. So a better mechanism is to use a system called interrupts. And with interrupts, the hardware devices actually signal the operating system whenever events occur, or more precisely, they signal the CPU, and then it's up to the operating system to receive and handle that signal. What the operating system will do is it will preempt any running process. In other words, it will switch what we call context away from that running process to handle the event. Basically, it will move the program counter of the CPU to the code to handle that particular interrupt. This allows for a more responsive system than we could ever achieve through polling without having to waste a whole bunch of time asking idle devices for data. However, this does require a more complex implementation, and that implementation complexity begins at the hardware level. Specifically, within the CPU, we need to have a mechanism for checking and responding to interrupts. And this mechanism is implemented as part of the CPU's fetch-execute cycle. In the process of fetch-execute, the CPU is going to fetch an instruction from memory, increment the program counter, execute that instruction. But instead of simply going back to the next fetch, the CPU actually has to have additional hardware to check to see if an interrupt event is pending. If there is an interrupt pending, then the CPU has to be switched to kernel mode if it's running in user mode So the privilege level needs to be escalated. Save the program counter by pushing it onto the stack, and load a program counter from a fixed memory location, and that fixed memory location is called the interrupt vector table, or IVT. So we load the program counter from the IVT, and then the CPU goes and executes that new instruction the next time the fetch execute cycle resumes. So the CPU actually moves from executing program code to executing code from the interrupt handler for the particular event. If no interrupt is pending at the end of an execute, then we simply go back to the next instruction, fetch. The interrupt vector table consists of an array of addresses of handlers. Each element in this array essentially gives the program counter location for the handler for a particular interrupt. Now, this handler is going to be in a subsystem of the kernel for a monolithic kernel, or this handler might invoke a call to an external server for a microkernel. In any case, however, the first handler by convention, element 0 of the array, is always the handler for the clock. Then handlers for different devices are in the array after the clock handler. So the interrupt vector is always mapped into the user part of memory. It's always available at all times so that the kernel can go and look up interrupt information whenever is necessary. An interrupt is processed by branching the program counter to the interrupt handler, executing the interrupt handling code, and then at the end of the interrupt handling code, there'll be an instruction to return from the interrupt. In the Intel assembly language, this is the IRET instruction, which loads the process program counter back from memory. It pops the stack to get the original program counter back, and goes ahead and changes the CPU back to user mode, so it removes the privilege escalation. The interrupt handling mechanism is thus able to handle events from hardware devices without having to poll each device individually to get data.